Hello, everybody. I will talk to you about UPF and RT flow, our favorite subjects. So I have to admit, when I got that last position, the last slot, I was a little bit disappointed. But on the positive side, you're all experts on UPF and on RT flow, which is the main topics of the subject. And this is from both Brian and me. Okay, so a crash course on 5G system architecture. If you're familiar with the 5G, it's based on the 3GPP standards. I picked up the 3GPP architecture from release 16. It includes a lot of functions. 3GPP is a whole different language. If you want to get familiar with the 3GPP language, you have to learn a lot of abbreviations and acronyms. So I took all the acronyms of the bottom line. If you look at the architecture, on the top layers, it's a lot of functions that are related to users management, to registration and management, control. The data portions, which we're all interested in, are at the bottom. So if you look from left to right, you have the UE, the user equipment, that's your handset. Then you have the RAN, that used to be the E node B and G node B. Now it's called the access network, or it's not even just radio access network. Then you have the UPF, which is the main subject of this discussion. And then the data network. The data network is not part of the 5G network. It's the, any network. Could be enterprise network or the internet. So the UPF is actually the termination point between the 5G network, the 3GPP defined network, and the internet. So they define names for everything. So we have the N3 interface, that's the GTP interface between the radio access network and the UPF. There's the N6 interface, which is just IP interface towards the internet. And then you have an N9 interface connecting what was shown in the previous lecture between intermediate UPF and UPF. UPF is the major item for manipulating the data, the packets of the 5G network. It's a user plane function. It collapses all the data elements of the 5G. So essentially, before 5G, you had two separate entities. You had the SGW and the PGW. The PGW was the termination point, the last point before the 5G network and the internet. And then you had the SGW, which was talking to various E node Bs and G node Bs and making the handovers between base station when you move. Now they introduced SDN. SDN is a new concept for 3GPP. They introduced it in release 13. And instead of SDN, they called it CUPS, Control User Plane Separation. So they split the SDN gateway and PDN gateway, the SGW and the PGW, to two entities. One is the SMF. SMF is, you can look at it as the SDN controller. And UPF is the switch element. And in between, you have the N4. N4 is a new interface. It's an SDN interface. It connects like the SMF, which is the SDN controller, and the UPF, the data plane element. But they invented the new interface. 3GPP like to invent stuff. So invented a protocol called PFCP. PFCP is for controlling the UPF functionality. Now we focus a little bit about around the UPF. So on the left side, again, you see the user equipment or any other endpoint. Could be connected cars or lots of other IoT devices. Then you have the radio access network, the E node Bs and G node Bs, and in the middle you have the UPF controlled by the SMF. So the UPF, there are two choices. You can put traditionally, PDN gateways were put at the data centers. PDN gateways used to be very large devices, terabits, large devices for large network, and this connected you to internet. But in the previous presentation, you just heard about the need for what's called local breakout. If you want to have in 5G very low latency and you want to have some data from the internet cached at a local point, then you need to break out at the edges. And this is a choice for many carriers. They can choose to put the UPF at the edges. And seems to be that this is something that's been catching on quite nicely. So it's called something like local breakout. You have a big UPF at the data center terminating all the data flows, but you also have distributed UPF, so you can break out to the internet directly at the edge. Now, this creates a unique opportunity because UPF at the edge is something that is happening at a small location. If you're familiar with the edge, everybody is right now speaking about the edge. Both the cloud providers and the carriers want to put a lot of server knowledge, NAV and servers at the edge. Then the edge has some unique features. First, the edge locations are small locations. It's usually not a big data center that you can place as many servers as you want. So it has a limited amount of servers you can fit into the edge. And it probably has some limitations of power and space. So you can put very small servers and limited amount of CPUs. So this calls for acceleration. If you have limited power, it makes sense to accelerate and offload several. You can put more if you accelerate, so you can better use your CPU cores. So the need for acceleration has been addressed. So this specific use case of accelerating UPF has been acknowledged by carriers around the world right now. In Mobile World Congress Shanghai, China Mobile did a demonstration, a demo in their booth where they're demonstrating offloading UPF by SmartNICs. And this has been right now, since China Mobile are leaders in this market, a lot of carriers are now trying to define, there's RFPs and RFQs of defining UPF at the edges, acceleration using SmartNICs. So this is a real-time use case, and right now it's a hot topic around the community and the industry. So what does the UPF look like? You already heard about some of the acronyms here. First thing that this is the way that an SDN controller, in this case the SMF, looks at the UPF. So the SMF needs to program things into the UPF remotely. The first thing it does is program the packet detection rule, that's the PDR. When a packet comes in, you first need to classify the packets and associate it with the user element, with the user and equipment. And that's the first rule that you hit. So it's usually a complex classification rule. And after you hit the PDR, they use something like pointers. Instead of telling you exactly what to do with this, they point you to a lot of policies. So the first policy is the forwarding action rule, the FAR, another abbreviation. Sorry for the so many abbreviations. So the forwarding rule tells you what to do with the packet, where to forward the packet, what MAC address you have to put. It's like a simple router, and maybe also have to, if it's a multicast, you have to replicate the packet. So this is the forwarding rule. Then you have what's called QER, the QoS enforcement rule. This means traffic management, shaping, policing, all the stuff that you have to do from maybe marking the packets towards additional routers. And then you have billing information, which the URR. By the way, there are lots of others. There's also a BAR, buffering action rule, puts all the queuing and stuff. So essentially, just to summarize all this crash course on UPF, it's a very complex equipment, and it has very flexible way that the SDN controller can program the UPF, the data pass element, using these structures. Okay, now moving to the second part. The second part talks about, up until now we've been just talking about standard stuff. This is nothing new. What we propose here is to formalize the offloading in the further separation of the UPF into UPF-C and UPF-U. That's the control plane and the user plane. Again, user plane function is essentially a data plane element, right? It's a software entity that processes packets. So we suggest to further segment it into UPF-C, which is a software element, and a UPF-U, which is the SmartNIC offloading the data path element. So this is not standard, this is our suggestion. So what you have here is on the left side, you have either usually GTP packets. On the right side, you have the data network with IP packets. By the way, it could be GTP on both sides using what's called intermediate UPF. And the SmartNIC and the hardware offload can offer some kind of acceleration method for the UPF to offload a lot of its functionality. So thanks for other lectures that were done today. We also had some presentation that's speaking about partial offload and full offload. So what is the normal packet flow? The normal packet flow, packet comes in, it goes to the SmartNIC, and maybe some acceleration towards the software, maybe policing or shaping or pre-classification, and then the UPF-C does all the packet manipulation and sends it towards the data network and vice versa. That's called partial offload, and this stays. What we suggest to do is what was described today as hairpinning. By the way, I didn't know the nice explanation about the hairpinning, so thanks for that. So full offload full offload means that all the packets will go from left to right only to the SmartNICs, and they do not need to go to the CPU. And as was explained today, this saves a lot of CPU cycles, saves a lot of CPU cores, and of course saves a lot of power. So this is only applicable for flows that are identified by the UPF-C as being offloadable, meaning it will try to push the rule into the SmartNIC if it's capable of doing so, and there needs to be some way to validate this. Just validating flow by flow is not very useful. But if and only if the SmartNIC can offload it, then all the packets can go from access network to data network, and no need to be processed by the CPU. So what are the features that we can accelerate if you partition the UPF-C and the UPF-U? So first, the UPF-C needs to do everything. So for packets that cannot be offloaded, it needs to do all the UPF functions that are fully defined. And then some functions remain in the CPU domain. For example, DPI or defining profile and all this, these functions remain at the UPF-C and at the software layer. But what the hardware layer can offer, meaning is the UPF-U, is full offload of things like the routing and forwarding, GTP, quality of service, traffic management, shapers, policers, packet duplication, replication, and also IPsec. Encryption is only needed, it's not defined in the UPF, it's another entity called non-3GPP interworking function. So it is required, and of course, encryption is very CPU intensive. This can also be offloaded in the SmartNIC. So this is a suggested separation between the UPF-U and the UPF-C. So now coming to the issue that was in the agenda of the topic of this presentation, what is the interface between the UPF-C and the UPF-U? So first, let's talk about some configuration. As you have to remember here, this is an SDN network, so all the configuration is done from the SMF towards the UPF. So nothing is learned. There's nothing automatic. There's no, unlike routing, there's no dynamic routing involved. Everything is configured from the SMF. The SMF is the boss. It decides everything. So a similar, typical use case would be for the SMF to send some rules to this N4 interface, the PFCP protocol that was defined. This is an SDN protocol. And this will define some PDR rule and FAR rule, what to do with the packets that would be associated with a specific user and a specific quality of service, QFI is called. So this would be processed by the UPF-C, and then the UPF-C would probably translate this into a dozen rules. It's not just one rule. Lots of, because, for example, the traffic management rules are different protocols, so we need to define policies. That's why PFCP is not simple. It's very complicated with lots of pointers. You have to point to an FAR rule. You have to point to a quality of service rule and all this. So this would be translated into several rules in the UPF. And there is a question here, how the UPF-C translates this information into the UPF-U. So what are the options? First options is to do in-band management. We can do control plane messages. So we take a few control packets received by the SMF, translate them to another protocol, and then comes to the question, what protocol should we use? You know, PFCP is complicated. It's not supported easily by the SmartNICs, so we need to define a new protocol. So first we can try and define some kind of new protocol, and the second option is just use an existing protocol. Another option is to use RTE flow. As you can imagine, this is what we think is more efficient and what should be the case, what we propose for the community to accept. So the control plane messages is an in-band approach. In-band approach means that you just use the interface that you have between the UPF-U and the UPF-C. This is a high bandwidth interface. It has gigabits of interfaces. So if you just use this to send information between the two entities, it will not consume a lot. It's just sending packets, translating from one packets to other packets. So what are the benefits? The first benefit has good performance, right? You don't consume, the control packets will only consume a small portion of the bandwidth from UPF-U to UPF-C, so this is not an issue. But since you want to invent a new protocol, a new standard, so you have to have a community for this. Somebody needs to bring up a new community, define a new standard. And it's not a simple standard. You have to address the issues of errors. What happens if the configuration fails? You have to address issues of how to define, for example, billing rules, and lots of other stuff that are not easy to define. And then again, you'd have to update this from time to time. You know, 5G group are known to have releases from time to time. I'm sure that they will have new features in the UPF, so if a standard group comes in, it will need to maintain the standard from time to time. Another option is to use an existing SD interface. You can take OpenFlow, for example, but it's not easy to translate what's needed between PFCP, which is very complex, into an existing SDN protocol such as either OpenFlow or P4. So our suggested approach is to use RTE flows. This seems like a very logical interface. So when some command from the SMF comes in, it would be processed by the UPF software, and the UPF software will decide if it can offload this or not. That seems to be, a natural approach. If you look at the market right now, UPF is a very network-intensive software. It has a lot of, it requires a lot of packet processing, so DPDK is the natural choice. I know there are a few use cases in open source we're not using DPDK, but I think the majority of the solutions that will implement UPF today are using DPDK. So RTE flow seems like the natural choice. We've seen right now that there's a wide variety of vendors already supporting RTE flows, and just need to make sure that all the functionality can be conveyed using RTE flow commands, and we'll see that it seems to be the case. There are some missing parts, and we'll touch that in a second. Okay, so now the nice thing about it, we heard very good presentations yesterday, and I want to thank the guys who did a great job. So by now everybody's know what RTE flow is about. I don't need to present it. The only thing I wanted to discuss here is push some ideas into the community to talk about things that might be improved in RTE flow for UPF. The first thing that comes to mind is performance. There was another presentation today about increasing the performance of the I4T. This is just one example. But UPF speaks about a large number of flows. You can think about a few million flows. So whatever you think about, whenever you think about populating a UPF with a few hundred of thousands of rules at a time, speed comes to mind. So the ability to improve and improve more the rate we configure and push information from in between the SmartNICs and the software is always room for improvements. So we're just saying that there is some, we're just suggesting a few ideas. It's not must, but we're calling for action to the community to try and come up with any suggestion that might be useful to increase the rate of configuration. One approach we're suggesting here is batching. So one idea could be, instead of doing RTE flow 1, 2, 3, and we've seen how this is processed today in the I4T, for example, instead of that, we can build a structure filled with I4T, RTE flow APIs, commands, and then push them in one command like a commit. So this can be a suggestion. Of course, you have to have some mechanism around it to report errors. So you will need to name you have to number the commands, and push errors, if any, into some commands. But potentially, you have the ability to push a large number of RTE flows in one commit. The same can be done for reading counters. You can build a large number of counters and then push them in one command towards the software from the SmartNIC. Another way is to maybe create an RTE flow template. UPF is very standard. All the users are usually the same. It's a large number of users. They all build the same thing. If you would build like an encapsulation RTE flow, and then you will need to populate the MAC addresses. The MAC addresses are usually the same for all of them, because they're just speaking between the endpoints, which are similar, and the GTP header is usually quite fixed. So the only thing that you would need to change is, for example, the UE IP address. and maybe the TID. So you can build a large structure and say, I want this template, and just set 2 variable fields. One something that we found missing is we didn't find the support for GTP incap and decap, GTP-U. There is good support for matching the GTP header and matching TID field, but incap and decap we didn't find. And there is also just noting that there is a GTP extension header. We've seen just now the GTP header is itself, so the last field in the GTP-U header is called extension header, next extension header. Usually right now it's 0, but it can point sequentially to others. So each, you can put another extension header, it will say what is the next extension header. So when parsing and removing the GTP header, you need to support this variable extension header. And specifically for 5G, there is the need for what's called PDU session container. The PDU session container is a must header in the 5G. This is the header that we have. So we have the QFI. The QFI is when populating, when encapsulating, we must add the QFI and some additional fields. And when decapsulating, need to be able to decapsulate dynamically extension headers. So that's it, and we'll stop for questions. Summary, oh, sorry. Last one slide. So what did we learn? UPF is a 5G element. It can be placed at the edge, and this is the choice right now. There is a need for hardware offload. It's been acknowledged by many carriers right now, and we think that DPDK RTE flows can solve this. And there are some modifications or enhancement can be done for RTE flow to match the needs for UPF.
If I may, some comments.
Good.
Can you repeat? Number of the things that you addressed that are missing are already present in the
Right.
RTE flow. For example, already we are implementing, it's per application, the structure to modify only the MAC, for example, or anything.
What?
Please return to your slide.
Which one?
No, the one that you wanted to, not Brust, yet a single RTE flow template. This can be addressed by the application itself, which we are already doing in some applications that create a template and just modify the relevant fields. It's already done and implemented in a lot of cases.
Okay.
First of all.
Thanks.
Second, regarding the NCAP and DCAP, you have the raw NCAP.
Yeah, raw NCAP does not. I know, but raw NCAP does not include the dynamic enhancement header.
It includes everything. You can simply set the buffer that you want.
True.
That's the idea.
You can do everything. You can do VXLAN with the dynamic header, but it's better to address the right fields. Why not just use GTP instead of, we can do, with the raw header, you can do VXLAN and GRE and whatever. So why not use specific names for GTP and add it? The raw header can do everything, right? But you don't have the names of the fields that you want. So it's better to use...
You have the buffer. That's the main idea, was that in order to... We had the VXLAN, we have another, and then we said there's a lot of other protocols and protocols, so we don't want to create an extra actions for each one. So just try to whatever buffer you want.
Today you have VXLAN and GRE. So, for example, when you decap, how do you decap it with the row if it's either extension header or no extension header? So there is no. It's a little bit tricky to read if there is extension header or not. I'm not sure how to do it with row, but you're right. Row can do whatever you want, but I don't see a reason why not. If you have VXLAN and GRE, why not use row device, row encapsulation?
We're using it.
What?
It's old API. We couldn't remove it.
Yeah, but you have a row. You have an encap and decap for VXLAN specifically.
Yes, it was the original one, and then we created a row, and we cannot remove the VXLAN. That's the reason.
You're right. You think row, you can use that.
But the burst idea is nice.
What?
The burst idea to write in configuration, but that supports.
Glad you like it.
So in the burst APIs, I imagine you want to have some higher insertion rates for flows. So what are the requirements for the 5G scenario you presented? What is the insertion rate you need?
So there's no real requirements, but as fast as it will be better, right? Since you have millions of rules, as fast as you can will be better. you can go to a customer and ask him what's the insertion rate. Everybody wants it to be as fast as possible, right? I don't have a number, but I'm sure that when something fails and you insert like 1 million rules, they would want it to be as fast as possible, right?
So the direction that we currently see in the DPDK is that burst API are quite difficult to define, specifically for the error cases and so. So what we see PMD doing now is just the accelerated insertion of a single flow. So as the Intel presented here, they can support millions of rules per second, and I know also Mellanox. So driver optimize their insertion rate and their counter query rates so that you can keep the simple APIs while having very high insertion rates.
Any questions? Okay, I have one question on the batching. So
on which one?
On batching of RTE flow entries.
Yes.
So this is a interesting point here, right? So we have batching for the data plane packets. That's well understood. There are tons of packets coming in, you batch them and process them. But here we're talking about control plane packets. And they're not going to be coming in as often as data plane packets.
No, everything is just data plane. So you don't need from an SMF, from the, let's go back. So when a packet comes in, the control packets are just coming from, they don't even have to come in band. The control packets are coming through a different interface.
Yes.
I'm just trying to think about when a control packet comes in, we understand it, how to translate it to rules.
Yes. So I understood that point. Now you are making a proposal that we should have batching of flow entry adds. So what that means is you need to collect, let's say, 32 control packets. So my question is, do we have enough control plane packets coming in within a given period of time?
When you get like an N4, for example, one packet usually could be translated to a lot of RT flows anyway.
Okay, great.
And also, you're right that you can get a lot of N4. It might be that you have to have a lot of calculation. This is just a UPF application. I'm just guessing because I'm not a UPF provider. I'm guessing that there is some processing time related to getting a lot of UPF commands and translating them. So in the meantime, you might be getting more. So I'm not sure about the rate of how fast you get N4 commands. This is out of band. So this relates to how much the SDN controller can fastly generate more rules.
Okay, great. Thank you.
Yeah, one more comment about batching. Usually, when we do batching, we introduce some latency. So the question is, which latency can we afford for such for flow configuration?
You're right. I'm not saying that batching is the best idea. This is just if you have, this is related to the previous question, if you do have already a large amount of flows that you want to pipe in and you're not able to push them, then batching comes into mind. If you don't have and you just have like one, certainly you don't want to wait until like a timer or something. Just only when you get some kind of say a stack of commands you want to push and you're not able to do that, then comes into mind, okay, so let's push them in a batch.
Okay, great. So we are at the end of all the sessions. Thank you so much.
Okay.